In the previous sessions, we had solved various numericals and we had tried to locate the centroid of various composite sections. Okay. So, now in continuation with that, let us move on to the next set of problems. So, wherein you will be having an opening inside a composite section. Let me show you how. So, the problem goes like this. In a rectangular lamina 100 mm by 120 mm, a rectangular opening PQRS (20 mm by 40 mm) is made as shown in figure. Find the centroid of the lamina after the opening is made. So, this is the question. In a rectangular lamina of 100 mm by 120 mm, a rectangular opening of PQRS of size 20 mm by 40 mm is made as shown in figure. Let me draw the figure. Find the centroid of the lamina after that cut is made. So, now let me write the figure. So, this is the rectangular lamina of size 100 mm by 120 mm. Okay. So, they have given the axis as well and this is the opening made. So, the size of this opening is 20 mm by 40 mm. So, this width is 20 and this distance is 40 mm. So, need to locate the center of this particular lamina after this cut is made. So, if I consider this as a rectangular lamina, so what is given in this problem is we have to make a cut. See, without an opening made in this particular rectangular lamina, the centroid exactly lies where? It exactly lies at center, which we have already proved. But will the location of the centroid remain same even after we cut this paper or cut this rectangular lamina? That is my question. If I cut a part of this rectangle, will the centroid be located in the same point? Okay. So, the answer is no. The centroid position will obviously change because there is an opening made. That means you have to deduct its area. You have to remove the area of the cut section. Okay. So, let me cut the section. Now I have removed this rectangular section. Now this is our figure. So out of the rectangle we have to cut this particular rectangle as given in the problem. So now we have to locate the centroid. So initially this rectangle was not having any cuts made. Now we have to cut a rectangle because it is given in the question, and we have to try to locate its centroid and the position of the centroid. Okay. So let us see how it goes. The very first step is look into the axis of symmetry if any, but since there is a cut here, we cannot say that we will be having a axis of symmetry. So that is ruled out. Second thing, we have to draw the reference axis. Okay. Then the third step is, if you have a composite section, divide this into number of known components whose centroidal values are already known to you. Okay. So here what we can do, instead of dividing, we can number two different rectangles. One is the bigger rectangle and the other is this cut made. So let me number those things. So this is component 1 and this will be component 2. Clear? So next, what is the step that is different in this particular problem compared to the previous ones? In the previous problems we were not deducting the areas, but in this problem we need to deduct the area whose part is removed. That is, the area of component 2 has to be removed while calculating the centroid. That is, we have to write a minus sign with the area. Whenever you try to write the area of component 2, you have to include minus sign or negative sign. Okay, let us see. So component 1. So now let us mark the reference axis. OX, OY. This is OX and OY. With respect to this coordinate axis, we need to try to locate the centroid. Okay. So component 1 is the bigger rectangle whose area is 100 by 120 mm. So A1 is equal to 100 into 120, which is 12,000 mm square. And what about the x component of this? For that, x component of this, y component, there is nothing but the centroid of the individual components. So let me write x is equal to, so this is 100 mm and this is 120 mm. So x is nothing but half of 100, that is 100 by 2, which is equal to 50 mm. What is about its y? It is equal to 120 by 2, which is equal to 60 mm. Now let me write component 2. A2. To write A2, I need to draw the figure also. mm and 40 mm. Try to locate the centroid of individual component. So A2 is equal to 20 by 40, but with a minus sign because it is to be removed. So which is equal to minus 800 mm square. What about the x component from the figure? It is half of 20, and for y component it is half of 40. No need to write a negative sign for these x and y components, because it is to be measured with respect to the reference axis or the coordinate axis. See, the sign conventions for x and y depends on from which axis you are measuring. If you are measuring x towards right, it is treated as positive. If you measure x towards left, it is treated as negative. Similarly, if you measure y towards up, it is treated as positive. If you measure y towards down, it is treated as negative. So, based on that, the signs of x and y needs to be written, but area has a negative sign because it is an opening made. Again I repeat, this particular step is not required, but it gives you a clear picture in order to write the centroids of the individual components. That will help you out, but taking this as a hint, you need to try to measure the centroid with respect to the reference axis or the coordinate axis. Okay? Let me write the table. So, the first column will be component, second component is area in square, third column is x bar in with respect to OY axis, and y bar in with respect to OX axis, and we have two different components here. So, component 1 is the, let me name the corners as A, B, C, O, and let me name this as P, Q, R, S, because this P, Q, R, S is given already. Okay. So, component 1 will be A, B, C, O, and this is the orientation. Next, what about the area, which we have already calculated? It is nothing but 12,000 square, and x component, that is x1. x1 should be measured with respect to the OY axis. So, this is OY axis. So, this is our x1 value. So, it is nothing but half of 100. x1 is equal to 100 by 2, which is equal to 50 mm. Now, what about its y1? With respect to OX axis is our y1 value, which is nothing but half of 120. So, x1 and y1 are now calculated. Now, coming to component 2, which is PQRS, and the orientation is almost similar to the previous component, and the area of the component 2, which we have already calculated, which is, if this is A1 and this will be A2, which is equal to minus 20 into 40 is 800, minus 800. Please be careful with this step. We have to write a minus sign, that is why I have drawn a star here, because the area has to be removed. And then what about x2? x2 is measured with respect to OY axis. So, since x is measured towards right, the sign convention says it is treated as positive. So, till this point you need to measure, and that is taken as x2. But in the previous step we had located the centroid of only component 2, that is this value, which was half of 20, 10, but you need to measure it from OY axis. So, from here to the midpoint you have 50, 100 mm by 2 is 50, and then what about the remaining distances? So, there is one more data given, which is this gap is already given in the question, which is 10 mm. Okay, this is already given in the question. If this is 10 mm and half of the distance of 100 mm is 50, and what about this remaining? If this is 20, 20 plus 10 is 30, the remaining will be, and this will be 20 plus 10, 30, 50 minus 30 will be 20 mm. So, if you measure it from OY axis, it is 50 plus 20 plus 20 by 2. Am I right? That is 50 plus 20, 70 plus 20 by 2. So, this is equal to 50 plus 20 plus 20 by 2, which is equal to 70 plus 10, 80. X2 is 80 mm. Similarly, calculate Y2. Y2 will be equal to measure it with respect to OX axis, but in the previous step we had tried to locate the center of only component 2, which was 40 by 2. Now, measure it from OX axis. So, how do you calculate this Y2? How can you calculate this Y2? So, the total distance from here to here it is 60 mm, and you know this is 40 mm. So, the remaining work distance is nothing but 20 mm. Clear? So, measure it from this axis until this point, that is Y2. So, from here to here it is 20, 20 plus 40 divided by 2, that is 20 plus 40 by 2, which is 20 plus 20, which is equal to 40 mm. Now, you have all the values of x1, y1 and x2 of y2. Now, substitute that in the centroid formula and calculate x bar and y bar. Let us see. What is the formula for x bar? It is a1 x1 plus a2 x2 divided by a1 plus a2. So, you might be wondering, I had written minus sign here, but I am writing plus sign here. I will not change the sign in this formula, I will write it as it is. But when I substitute the value of a2, then I will be writing the exact minus sign. What happens if I change this sign here? It creates confusion. If I write minus sign here, you might write minus sign and again in bracket minus a2. That is why I will be writing this as plus, and then while substituting I will be writing the value of a2 as minus. Okay, let us see, which is equal to a1 is 12,000 and x1 is 50 plus what is a2? It is minus 800 into x2 80, 50 and 80 divided by 12,000 plus minus 800 in bracket. So, when you try to divide this, it will be 12,000 into 50 minus 800 into 80 whole divided by 12,000 minus 800, and the answer will be 47.2 mm. So, this is the value of x bar. Similarly, we shall calculate what is y bar. So, y bar is given by a1 y1 plus a2 y2 divided by a1 plus a2, and a1 is already 12,000, whereas y1 is 60 and a2 is minus 800, y2 is 40 whole divided by 12,000 plus of minus 800, which gives us the value of 62.2 mm. This is the value of y bar. So, x bar is 47.2, y bar is 62.2. Clear? So, now after you determined the values of x bar and y bar, now you have to locate those values in this lamina, that is in this figure. So, x bar is equal to 47.2, y bar is equal to 62.2, that is the final answer should be written as, therefore, the location of centroid or the coordinates of the centroid, that is x bar and y bar, is equal to 47.2 comma 62.2 mm. That is, so x is 47.2, so this is 50, 47 somewhere lies here, and y is 62.2, so this is 60 and somewhere here 62.2. So, this is the point where the centroid is to be located. So, now we can draw the centroidal axis xx and yy. Now, just compare this with a regular rectangle without an opening made. If they consider the same problem, let me show you. If this is 120 mm and if it is 100 mm, where does the centroid of this rectangle lie? It exactly lies at center. With the values of x bar and y bar being 50 mm and y bar being 60 mm. So, this will be the centroid for a regular rectangle without an opening. Since we have made an opening in this problem, the centroid is not same, it varies. Because of this opening, the area has to be removed. The centroid is located as shown. So, now I think you get a clear picture when an opening is made in the lamina, the centroid positions varies. How the centroid position varies? Just compare these two figures. This is without an opening, this is with an opening. So, I had shown you the paper as well. Initially, this was a rectangle without an opening made. Now, since we have made an opening here, that makes the centroid to be located at a different point. I hope you have understood this. So, we will be discussing similar problems of this kind, wherein we will be having a opening made in the composite section. Okay. If it is a regular composite section without an opening, it will be very easier to solve. Even though if you have an opening, it is easy, but you have to write the area with a negative sign. Please note this, it has to be written with a negative sign, and when the coordinate value, that is x and y, will be written with a negative sign is, it is dependent on the reference axis and the coordinate axis. Whenever you write the coordinate axis according to your convenience and measure the distances of x and y, then depending on that you have to write the signs of x and y. Please be very careful regarding the regular section and the section with an opening made. I hope this is clear.